in this case. As a market maker, I'm going to create one security for each horse and sell these securities using a pricing function and kind of let the market trade these securities. The way that this mechanism elicits predictions is that if, let's say, the security C, which is like the top horse winning, is trading at, right now trading at like 0.5, but I have a strong feeling that it's going to trade, it probably wins at, it's going to win the race at probability 0.6. I'm going to keep buying without any budget constraints, I'm going to keep buying this security until the price of the security reaches 0.6. So from the act of buying these securities, I'm kind of revealing my internal belief about this horse, that horse winning the race. So the market maker is able to aggregate all these beliefs, and that's kind of the main function of a prediction market. But I did say there should be a mechanism to price these securities, and the econ.cs literature agrees that the best way to do that is through what is called a cost function, which is just defining a function C that's convex, increasing, and once invariant. The way the market proceeds is that if the total number of securities sold so far is Qt minus 1, which we call the state of the market, and a trader comes in and requests a bundle RT, the new state is kind of just Qt minus 1 plus RT. And in order for the trader to get this bundle of securities, the market maker is going to ask for C of the new state minus the C of the old state in cash to be paid to the market maker. But why am I saying that these two are equivalent? That these seem like very different settings and very different objects, because in prediction markets, you're trading securities for cash. But in CFMMs, you're trading between assets. In prediction markets, the main purpose of creating the market was to elicit forecasts about a future event. Well, whereas CFMMs was just a platform to enable better trading between assets and facilitating good trading mechanism. And in prediction market, any bundle could have been requested by the trader for a certain amount of cash, but in CFMMs, the available trades was like super restricted by an indifference curve phi. And it was actually believed in a literature that these two entities diverge by any desirable amount, which we actually showed that it doesn't. We show that there is a strong equivalence between these CFMMs and cost function market makers. And by equivalence, we mean that if one follows these reductions, if you start out with a CFMM, you can create a cost function market maker using this reduction that kind of performs in a similar, the market proceeds in a similar fashion as the CFMM would have. So the set of available trades after a given history are the same in these two places. I'm going to very briefly mention the proof idea. So if you have a prediction market and you want to create a CFMM, what we do is we use this trick that since we are dealing with Arrow-Debreu markets, which is to say that the securities that are available in the market are mutually exhaustive and mutually exhaustive and exclusive. So a $1 of cash is equivalent to buying one of each security, because if you do that, you're kind of guaranteeing $1 irrespective of what outcome happens. So we actually convert a prediction market into what we call a cashless prediction market using this trick. And that actually helps us in just somehow magically getting a CFMM. This kind of like the math works out. Okay, you can trust me on this. So that's like the super short summary of the proof in one direction. The other direction is also quite interesting. We are saying that if let's start with a CFMM, and you want to find a cost function that kind of behaves the same way. that's the CFMM, and let's say if the new state that the market is going to end up in is Q, we want to define the cost function as the amount in one's direction by which you would bring back the Q to kind of preserve the phi value before and after these trades. So that's kind of what this equation actually just says. So I only actually explained you what that equation is and not really given a proof, but I'm happy to talk about it later. So the more important thing of this result is I'm more excited about the implications of this result than the result itself, which is where I'm going to focus most of my time on. Before I jump onto the first implication, the equivalence was only like one result, and I'm going to talk about slightly another result because it's kind of important for the implication. So we started the project by asking like, why, if you're going to implement an automated market maker, why are people using this like weird indifference function phi? Are there better ways that we can do the automated market maker? And we try to solve that using just proposing some basic axioms for some effective trading. I'm going to talk very briefly about these axioms. So the first is no dominated trades. It just says that if the market is going to offer a trade, why offer a strictly worse off or a strictly better off trade also at the same time? Because no rational person would actually choose the worse off trade anyway. So might as well like restrict it to a point instead of like a set. The second axiom is path independence, which says that if you perform a trade R and then immediately R prime, it should be the same as performing R plus R prime, because you don't want to create a market where it might be profitable for a trader to split up their trades. It just creates unnecessary burden on the market maker. The third axiom is liquidation, which just says that if a trader comes in to the market as wanted to sell a bundle in exchange for another bundle, there should be some fraction of the other bundle you should be able to give. This just encourages better market behavior. The fourth is demand responsiveness, which just says that the price needs to respond according to the demand. Hopefully, these are quite basic things that we expect from a well-functioning market. And we show that a general automated market maker satisfies these four axioms if and only if it's implemented using a CFMM with increasing concave phi. This is a really great justification for why people in DeFi have been using these entities. For prediction market folks who know this result, there is also literature that dates back to 2013 that says that if you start with a general AMM and impose some really basic elicitation properties, you end up with a prediction market with convex one's invariant cost function. I also just said that in our paper, we show the equivalence between CFMMs and cost functions. What this implies is that desirable market-making properties are much more tightly correlated with elicitation properties. So whenever you think of any information loss in a trading platform, it kind of affects the price discovery. Before I go into the second implication, I'm going to talk slightly about the scoring rules. It's just a payment function that pays agents for making a prediction be about a future event. And when the outcome of this future event is realized, the agent is paid using that function. A scoring rule is said to be truthful and and is a proper scoring rule if and only if it's incentive compatible for the agent to just reveal their private belief and not misreport. There is also another class of automated market makers called market scoring rules that was proposed by Hansen, which actually rewards an agent to move the current market prediction from PT to PT plus 1 using this payment rule. And there are results that show that cost function market makers are equivalent to market scoring rules. And again, if we combine this with our equivalence, we show that a CFMM has a unique proper scoring rule associated with it. And it actually just runs a market scoring rule, which is really nice to think about. But what is it eliciting? It's literally trading assets. So we show that it elicits ratio of relative valuations of assets. So if you remember the Uniswap, which is the product function, if you use this if you use the equivalence and find the cost function associated with that product rule, you get something that looks like this, which is not so important, but the important part is that this actually appears in Chen and Pennock 2007 and is the constant log utility market maker that has been proposed 15 years ago. If you find the corresponding scoring rule that's associated with this cost function, it also looks something like this, but it's called the boosting laws, and it appears in Buja et al. 2005. So we have known about these markets in like a very different context, but our paper kind of brings everything together and connects all these paths. So that kind of nicely goes into the last implication, which is that we have connected in a really nice way decentralized finance and constant function market makers and also prediction markets, allowing for these literatures to go from one to the other pretty easily. So this is more of a pitch for future work because there is a lot we can learn from each other. So for example, DeFi could learn from prediction markets about how to design new CFMMs with desirable properties because scoring rules are much well studied. There are also really cool market makers in prediction markets called volume parameterized and profit charging markets, which would be interesting to see what kind of CFMMs they produce. And what's the parallels between CFMMs and online learning paradigms. How does the market learn in a no-regret fashion? So, but what can prediction markets learn from DeFi? There is a lot of DeFi research that is more focused on designing optimal CFMMs and how to impose the fees in an optimal way, trying to optimize for some other desirable feature of a market. So this is a kind of research that to my knowledge, does not exist as much in prediction market, and we could learn this from DeFi. The second really cool innovation that to DeFi's credit happens is liquidity provisioning. So when I said market maker, it had another function of trying to accumulate all the assets that were needed for making all those trades happen. So that's the way we use liquidity here. So instead of just market making having that huge responsibility of bringing in all the assets, the innovation is that this function is kind of outsourced to other agents. So we, in a future work, we actually do use this equivalence in a huge degree and kind of generalize this, how agents provide this liquidity and broaden the framework that DeFi has been using. And we greatly simplify, and this helps greatly simplify how prediction markets could also adopt this framework. So this is a cool innovation that prediction markets should bring in. So I'm gonna skip over the third result we have, which is trying to impose a bounded reserves, because if you directly use the equivalence that I gave you, it could end up in weird notions where like you do end up in a negative quadrant, which doesn't make sense as much in an asset world, but it does make sense in a prediction world. So we do modify the equivalence we give and give this construction, but that satisfies really cool properties. And we also show that every concave increasing one homogeneous CFMM is actually a result of this construction, and this is pretty much all the space of the practically used CFMMs. So we say that all the practically used CFMMs are actually coming from this construction. So just to like super quick recap, we generalize an ideal market maker as a CFMM. We show that CFMMs are equivalent to prediction markets, and we give a construction of a resource-aware CFMM. That's almost all the CFMMs used in practice. And there are some other cool directions that one could explore. That's all I have. Thank you.